Moncrief's Topological Space, Chapter 2. In this chapter, we're going to talk about topological space and continuous functions. The concept of topological space are coming from the study of real line and Euclidean space and the study of continuous functions on them. So first of all, note that if R is the set of real numbers, then R to the m denotes the set of all m tuples of real numbers, and we usually call it Euclidean M space. In this chapter, we're going to talk about different methods, different ways to form topological space on a set. We're going to talk about open and closed sets, limit points, continuous functions, and so on. So, what is a topological space? Definition. A topology on a set like X is a collection tau T of subsets of X having the following three properties. First of all, empty set and X, this original set itself, are members of this collection. Second of all, this collection is closed under arbitrary union. It means that if you take any random subsets of X, the union belongs to this collection. And it's also closed under finite intersection. It means that any finite intersection between elements of tau is also a member of tau. A set X, along with this collection tau T, is called a topological space. We usually just eliminate tau and we say that, hey, X is a topological space. If X is a topological space, then we say that a subset U of X, we know that set X has a lot of subsets. We say that a subset U of X is an open set of X if U belongs to this topology. By using this terminology, we can say that a topological space is a set X along with collection of subsets of X that we call open sets, such that empty set and X are both open. It means that members of topological space, and the arbitrary unions and finite intersections of open sets, or those sets that are in tau, are also members of tau, or they are open sets. Example 1. So let us begin by taking a set with only 3 members, A, B, C, in that set. We're going to define different topologies on this set. So consider the first figure. The first figure consists of A, B, C, which are members of X. So it is set X along with empty set. The second set, the second collection here, includes a set X, A, B, C, a subset including A, B, and another subset including just one element, A. Take a look at this figure here. This is a collection of sets including X itself, a subset including AB, another subset including BC, and a subset which includes only one element. Let us see what's going on here in this figure. So the possible topological space for this set is collection including X. Empty set is always a subset of X, and the first subset including A and B, second subset including just B, and the last subset including B and C. Let's check to see if this guy is actually a topological space or not. The first condition says, okay, this topological space must include X, must include empty set. As you can see, both of them are members of this collection. So we're good with the first condition. The second condition says it's closed under any arbitrary union. It means that if I take the union of any sets here, it must be a member of tau itself. Union between X and empty set is X, which is into union of X, and any of these subsets is also a member of 2. So X union with A and B is X itself, which is into as well. So you can take the union of X with any other members here, and you can actually see it is equal to X, and it is a member of 2 itself. If you take the union of AB and B, it's equal to AB, which is actually a member of 2. You can take the union of B and B and C, which is BC, which is again a member of 2. You can take the union of AB, B, BC, which is equal to ABC, which is equal to X, and also again is in 2. So it's closed under arbitrary union. You can just continue forming all of these combinations between these sets and actually see it's closed under arbitrary union. Last condition, finite intersection. So I can take the intersection between X and empty set, which is empty set belongs to 2. I can take the intersection between X and any other members here, A and B, which is again in 2. I can take the intersection between AB and B, which is again in 2. I can take the intersection between AB, B, BC, which is B, which is again a part of 2. And you can continue this process, and actually this collection satisfies all of these conditions, and it is actually a topological space. Each of these figures form a topological space for set X. Do we have a collection that is not a topological space? Yes. Take a look at these two figures. For example, the first one says, hey, I have X in, I have empty set, I have a set including just A, another set including just B. So first of all, the first condition is met. It has X, it has empty set. Let us check the second condition. It must be closed under arbitrary union. So I'm going to take the union between these two sets with only one element, which is equal to A and B. As you can see, this set is not a member of this possible collection. So the second condition is not met, and it's not a topological space. Take a look at this figure here. This includes X, empty set, a set including A and B, a set including B and C, and that's it. So the first condition is met. You can see empty set and X, both of them are members of this collection. The second condition, okay, let us move forward to the third condition, check to see if it's closed under finite intersection or not. Take a look at AB intersection BC. You can actually see the intersection is equal to B, which is not a member of this collection. So the third condition is not met, and it's not a topological space. Example, if X is any set, the collection of all subsets of X is a topology on X, and we call it a discrete topology. So a discrete topology is a topology including all of the subsets of X. If you remember power set of X, this is a topology on X, and we call it a discrete topology. Another topology on X is a topology including just two members, X and empty set. We call it a trivial topology or indiscrete topology. Both of them are forming topological space for X. Example 3. Now consider this collection of subsets of X, to sub F, which is the set of all subsets of X such that the complement of U is finite or the complement of U is equal to X itself. We want to show that this collection is actually a topological space on X. Let's check the first condition. Do we see X, an empty set, as members of tau of F? Very well. X is a subset of X. Now, X minus X. You know that X minus X, or the complement of X in X, is empty set. So we know that empty set is a finite set. So this is met for X. So X belongs to tau of F. Let us check empty set. Empty set is a member of set X. Now X minus empty set. X minus empty set is equal to X itself. And we can actually see it satisfies the second condition here. So both of them are members of this collection. Now let us check to see if it's closed under arbitrary union or not. Suppose we take a collection of subsets of X. Our goal is to show that the union of these subsets is a member of this topological space. This is our goal. So let us put a question mark here. Very well. We know that if this union is a member of this collection, this union must satisfy either the complement finite or the complement is equal to X itself. Very well. X minus union of these subsets. If you remember De Morgan's law, it is equal to the intersection of the complements. Very well. We know that each U sub alpha is a subset of X and it is a member of tau of F. It means that X minus U sub alpha is either finite or it is equal to X. If it is equal to X, it means that U alpha is empty, X minus empty is X, the intersection of X is equal to X, and we're done. So suppose X minus U alpha is finite. So this is like this, X minus U1, intersection X minus U2, intersection, it continues. Each of these sets are finite sets. The intersection of finite sets is also finite. So we're done with showing that the arbitrary union of elements are also a member of tau of F. The last condition. Suppose we take a collection of subsets of X. Our goal is to show that it is closed under finite intersection. We want to show that the intersection, finite intersection of these elements, also a member of tau of F. So let us put a question mark here. X minus intersection U sub alpha, again by using De Morgan's law, is equal to the union of X minus U alpha, and X minus U alpha is either finite or it is equal to X. Again, if it's equal to X, you have empty set, you don't have anything to worry about. If X minus U alpha is equal to a finite set, we are taking the finite union of finite sets. The finite union of finite sets is also finite, and we're done. We just showed that tau sub F is a topological space. We call it a finite complement topology. Example 4, let X be a set, tau sub C be the collection of all subsets u of x such that x minus u is either countable or is all of x. So in previous example, we worked with finite subsets. Now we're working with countable ones. Then tau sub c is a topology on x. So we can define this collection, tau sub c, to be the set of all subsets of x such that x minus u is either countable or x minus u is equal to x. We have to check each of these conditions for this collection. So first of all, check to see if x and empty set are members of tau sub c. Obviously, x minus x is equal to empty set, which is countable. X minus empty set is equal to x. So the second condition is met. 2, we need to show that it's closed under arbitrary union. So suppose you take a collection of subsets of x, which are members of tau c. We need to show that the union of these collections of subsets of x also member of tau sub c. So let us put a question mark here. X minus union of u sub alpha, which is equal to the intersection of x minus u sub alpha. Again, if x minus u sub alpha is equal to x, u sub alpha just empty set, and x minus empty set is x, so the intersection is nothing but x itself. If x minus u sub alpha is countable, you have the intersection of countable sets. It's like writing it this way: x minus u sub 1, intersection x minus u sub 2, intersection with countable intersections of countable sets, which is countable. And finally, the last condition, 3, we need to show that for any collection of subsets of x, any finite intersection is also a member of tau sub c. So our goal is to show that this intersection, finite intersection of these collections of members of tau c are also a member of tau c, belongs to tau c. Okay, again, we are working with x minus the intersection of u sub alpha by using De Morgan's law. It is union of x minus u sub alpha. Finite union of countable sets, which is countable. So we just proved that tau sub c is a topological space on X.